I'm going to say let's go ahead and get started. I'd like to thank our attendees for joining today for our weekly MECI Alliance seminar series. My name is Teresa Worth. I'm the program manager of the MECI Alliance at MIT's Department of Mechanical Engineering. I'm here with Irina Gazieva, who's our program assistant, and Dr. Brian Anthony, our program lead, will be joining us later today to help with our Q&A at the end.
I was able to.
Okay. You just got in. Hi, Brian. Welcome.
Hello, all. Thank you.
Yeah. From all of us, I would like to welcome Dr. Svetlana Borskina to our seminar today. Dr. Borskina is a physicist and engineer who studies light matter interactions at the nanoscale and develops new smart materials and devices for solar energy harvesting, personal thermal comfort, night vision, space exploration, and biochemical sensing. She leads a research group in our Department of Mechanical Engineering, and we're very honored to have you here today, Sveta, my friend, to give this presentation. So thank you so much. I will pass the presentation over to you. While you get your slides up, I'll just invite our attendees to note that there is a Q&A function in this webinar today. So throughout the presentation or at the end, if you have any questions, please feel free to type your questions into the Q&A, and Brian will facilitate questions at the end. Thank you.
Thank you so much, Teresa, for the nice introduction, and thank you all for joining us today to talk about our quest in meeting and where we can preventing new challenges in biochemical sensing. So we are trying to work on the most pressing problems for the society, and of course, new threats emerge all the time. And this is a story of resilience in a sense, and our nimble approaches to try to refocus our research to address the new challenges by using the techniques we have developed before, and in some cases developing completely new techniques because the old techniques are not up to the challenge, unfortunately. So before I move into the actual talk, I would like to acknowledge the contributions from many people who work on different aspects of research that I will talk about today. So this includes students at MIT, and also our collaborators at Woods Hole Oceanographic Institute, at Rochester Institute of Technology, at Scifox, which is a small startup company in Cambridge, and also at Vanderbilt University. So this is a collaborative work, as a lot of work is today. It requires experts from many different disciplines, in this case, including optics, photonics, plasmonics, biology, chemistry, and what's not. And industry input is very important if we want to really make a change that can be applied immediately, or at least in the near term, and help people worldwide. So what are those challenges? So before pandemic started, now we have this obvious elephant in the room, but there are other challenges that are still there and used to be there before the pandemic started. So one of them, there is a big need to sense globally a presence of methane and other gases, which can be harmful gases or greenhouse gases in different environments, including sea and ocean water. This presents obviously a big challenge because water is distributed all over the planet. In some places, it's very hard to access, and you need to cover such large areas to actually detect something useful. Another major challenge that is there and is increasing is microplastic pollution. Again, a lot of it is present in ocean waters, and it keeps increasing because of all the trash that gets into water, and it eventually gets broken into tiny little pieces, and we don't even know what those pieces are in different places, and it's very important to be able to detect them reliably. And ultimately, of course, we believe it's more important to prevent this from happening rather than trying to chase this plastic around. And even if you identify it, so then what? Because you still need to remove it somehow from the ocean. So that's a big, big challenge. And I'll talk about it at the end of the talk. But then, of course, pandemic happened, and COVID-19 situation moved everything else to the back burner. And it really put upfront the need for rapid deployment of robust sensors that can be used by everybody, ideally without any specific knowledge. And in some cases daily or bi-weekly, as many people who return to labs at MIT know, they have to go through the procedure bi-weekly. So for those of you who don't necessarily work with biosensors, just to remind you the main elements of any biochemical sensor. So you have a sample where you may or may not have some material present that you are actually trying to detect, whether it's microplastic or methane or SARS virus. So then you need to capture it with the receptor to recognize that that's the material you are looking at. Then you need to have a transducer in your sensor that will convert this signal from a capture to some signal that you can actually read out. It could be optical signal or electrical signal or anything else that you can convert and process and understand and quantify. In most cases, you also need to amplify that signal, and I will talk about it a lot today, because especially if you have not enough target in the sample, it's very hard to get the signal, or if you get the signal, to distinguish it from the noise, because there is always noise, especially in biological systems. And then if you manage to get all these steps, you get your signal, and if there is a target present, you get result. Okay, yes, the result is positive. In the most ideal situation, if your sensor works perfectly, it's calibrated and gets you required amount of amplification, you should also get not only positive result, but negative result reliably. If there is no virus or plastic or what's not, you get a negative result as an outcome. It doesn't always work this way, unfortunately, and we'll talk about how we can make it work this way by using different techniques. So I'll start with the dissolved methane sensor case study, because this is something that historically came first. And also it shows you a case of a student that had to shift her research focus from something she was hoping to do, and that was spending her summer in Arctic on an expedition to test methane concentration in Arctic waters. But then because of COVID, everything got derailed, and she decided to focus her attention on, so her name is Morgan Blevins, and she is an MIT student and also a student at the Woods Hole Oceanographic Institution. And she decided to focus her attention on one aspect of sensing that was not ideal. So this is how a standard methane sensor looks like. Most of them are really large devices, and they need to be deployed with special platforms. And it's hard to have many of them because they are also expensive. But if there is a need to test everywhere and constantly, you really would like to have a small sensor that can be adapted to handheld use combined with a cell phone, for example. So you can deploy not just one student to the Arctic, but many students to local rivers or oceans to do testing. And so instead of going to the Arctic, she spent her spring and summer designing a new sensor. And she came up with a very nice design. The sensor is very different from the commercial sensors that most often use mid-infrared lasers, which are quite expensive and bulky equipment to do spectroscopic detection of methane. Instead, we focused on a purely optical detection that can be done in the optical spectral range. It provides high selectivity and sensitivity. And what's important, you can have a sensor with a very small footprint. So the footprint of a sensor is really thin. It's a couple of microns thin, and it can be a few centimeters in size maybe. And then it can be combined with a standard off-the-shelf cheap light source and another standard cheap photodetector. And both of these components can actually be found on a cell phone. So our final dream for this device is to be integrated completely with a cell phone. And the detection is done by simply looking at the changes in the reflectance, intensity of the reflected signal that is measured by the detector and comes from the LED. When some molecules of methane got embedded in the polymer matrix. And when that happened, we measure the shift in reflectance. And the shift that we have with our design is, as you can see on this plot, is significantly better than the only other, as we know, more or less portable commercial sensor, which is based on the surface Plasmon resonance. So you can see that if you want to have a sensitive detector, you want the slope to be as high as possible. So any change in the presence of methane concentration should result in a large change in the intensity of the reflection signal. And this is what our sensor provides. And what is more important, we can calibrate it by very simple changes in the sensor itself or in the interrogation mechanism, just simply changing the angle, for example. We can tune it to a desired concentration, because sometimes you have a situation where you know that the concentration range is going to be very narrow, then you want to have a very sensitive sensor, very high slope. But in other situations, we know it's a more broad range. So if we make our sensor too sensitive, it will actually become saturated after some measurements, and then you cannot see anymore. You cannot quantify what is that concentration. So the great feature about this new sensor, we can actually calibrate it, and we can use it for situation where we expect a high concentration of methane in the environment, or where we expect a very low concentration, and then we need to be super sensitive. So Morgan is working now making the sensor, and we hope to be able to test it soon. But in the meanwhile, there is this obvious other threat that emerged in the spring, and it put the need for this huge amount of testing that needs to be done daily, and not in the ocean, in everybody's house, ideally. So people don't have to drive to testing centers and then wait for days for the result to be released. But if you just calculate the sheer amount of people in this country, let alone worldwide, so if you would try to test every US person weekly, so that's more than 1 billion tests per month. This number is just mind-boggling. So you really need a technology that's robust, cheap, compact, and can be deployed to every person, ideally to their houses, or at least to the point of care where they can get results immediately. So this is the culprit that we're trying to find. So it's hard, it's very hard to detect the presence, as we already know from a lot of testing done over the last few months. The problem is it's a very small molecule. At the initial stages of it, it could be very few of them present in the organism, so it's hard to detect at that point. And also, it looks very similar to a lot of other flu-like molecules, including the common flu or the Spanish flu that caused a lot of deaths a century ago, and another deadly variety that happened in the previous decade. So all of them are about the same, all of them are coronaviruses, all of them are about the same size, made from about the same type of biological material, with the same dielectric constant, which is a useful signal for optical detection, because this is what we are actually detecting, the amount of material and how much of a change for an optical signal propagation it introduces. And that is defined again by the size and by the dielectric constant. So all the biological materials have very similar dielectric constants, so it's extremely hard to distinguish them from each other. And actually fluids in which we are trying to detect them, such as blood or saliva, they also have very similar refractive indices. So they are nearly invisible. Of course, there are differences in between these different strains of viruses, and that's why some are more deadly than others. But those differences happen on an even smaller scale. So that's an RNA within the virus and some proteins in the viral shell, which are different from virus to virus, but now their scale is even smaller. And you also need to extract this material from the virus, a viral particle first, to actually test. And just how smaller? So if we put this on a scale, so virus on itself by itself is small, DNA or RNA in this case within is even smaller. So this is nanometers on this scale. Proteins are even smaller. And if we're trying to interrogate with light, which we do with the optical sensing mechanism, so light has very small wavelengths, but still visible light. It's still in the hundreds of nanometers in length. So it is larger than the virus. So you can see that when a light wave is passing through, say, one viral particle, it introduces very little contrast. It's very little scattering object to actually fill. So you need to do something. And in most cases, the problem is the false negative result that your sensor gives you, because it's just not enough material. You cannot see the amount of the material. You cannot distinguish it from the noise. which is defined by your detector sensitivity, and also presence of other materials in the sample. In some cases, however, you can have an opposite situation. You can get a false positive, where your system says, okay, there is a virus when there is no virus. And this is something that happens with the more standard test in use today, which is PCR test. So if you did testing for COVID, that's probably the test that you had to do or was done for you. And this is a recent article from New York Times that highlighted the problem with this technique, that it can actually overcount the number of cases because of how sensitive it is, because of mechanism that is behind this detection. So what is that mechanism? This mechanism is biological signal amplification. So if the problem is that you don't have enough material to start with, the solution in the PCR test is just make new material, make more with. So how it's done? It's done through creating copies of virus RNA by combining them with complementary DNA copies and adding more and more material in the mix and running it through multiple steps of creating new and new and new chains. So usually it takes about 30 to 40 even steps. And at every step, so this is geometrical progression. So every time you double the amount. And so you can see that by 30th iteration, you have huge amounts of those copies, which of course makes it easier to detect because now you have so much material, but also it increases chances of an error because you can amplify, if you amplify that much, you can accidentally amplify noise, some virus that is not actually posing a threat. Also, of course, this long procedure, that's why it also takes so long. So it increases time, it increases cost, it has to be done by specialists, and it makes the system more complex. It also requires some additional steps within, a lot of washing and mixing of liquids and thermal cycling. So every one of these steps requires thermal cycling to 2 different temperatures. So, but it still works, but the idea is to do better somehow. So people working in optics and photonics, obviously not just us, but others too, they refocused their effort and started looking at repurposing optical sensing platforms that has been developed before for different types of sensors to sense COVID. So these are the 2 recent examples. So one on the left is a published results on a surface plasmon resonance sensor for sensing COVID, and another one is a work done within the European project where they're trying to repurpose the interferometric sensor, which is a very well-known sensor platform for sensing COVID. So why do you want to use optical sensors in the first place? So there are several reasons. So one is you can add optical signal amplification. So instead of doing biological amplification, you can try to amplify the signal as much as possible. So that's something that we did with our methane sensor too, when you have not a big change in the environment because of the presence of gas or molecules. You're just trying to recycle the light many, many times within the system. And at each cycling time, the light senses the presence of this biological material or chemical material. And you can accumulate this signal to create a larger outcome. So instead of amplifying the amount of material, we are amplifying ultimately the time that light spends interrogating this material. Another obvious advantage is the sensor miniaturization, because if we want to deploy 1 billion sensors monthly, they better be small enough so somebody at least should be able to make so many, and the material should be available to make so many. So optical biosensors allow this to happen, but still, if you have very little material, even if you provide optical signal amplification also amplifies noise. So it may not solve your problem completely because both of the signals get higher, but what you're interested in is actually the ratio, is signal to noise ratio. That's what's important. So another platform that we are pursuing as one of our approaches, and which is already well developed for semiconductor industry, obviously, is silicon integrated photonics. And it certainly provides miniaturization. So if you take a standard 12-inch silicon wafer, you can actually make 50,000 disposable test chips from this one wafer. And one foundry, which are multiple foundries around the world, produce a lot of wafers monthly. So in principle, if you dedicate one foundry just to make chips for this type of sensor, you can have 5 billion tests per month. So it is in principle doable, and the cost of each chip will be really small. It's like under $1. So it will be affordable for people to use it. But we still face the same problem as with other type of optical sensors. So one typical integrated type of a silicon sensor is a ring resonator. So how it works, so you have this ring, it could be disc, it could be some other shape, it's just ring as a very standard high Q platform. So you bring light in through an integrated waveguide, then it couples into the resonator, it oscillates multiple times, and then the signal leaves through the same or sometimes another waveguide. And you monitor the intensity of the light emergence from this output channel. So this is how it looks like if you take a snapshot of the field distribution within this system. So light comes in, it forms this rotating mode in the ring, and then it leaves. And then what you actually detect, so this is the signal that emerges on the output channel, and it features some very sharp resonant features. So these resonant features are because of this type of resonance that can be excited in the ring. It only happens at certain frequencies, not at every frequency. And the spectral range where this resonance happens is very narrow usually. It's sub-nanometer spectral range. And then the standard way, which is used in all the existing silicon photonic biosensors as far as we know, and also the two platforms I just showed you that people developed for COVID-19 sensing. It works the way that there is an initial spectrum, and then you capture material. So you have some receptors on the surface that selectively capture whatever material you're trying to sense. So in this case, it's viral RNA, for example. So the receptors in this case could be those complementary DNA pairs that the same as used in the PCR test. And then the presence of this captured material shifts the spectrum to usually longer wavelengths. And what you detect is this shift. But then if you don't capture enough, if there is not enough of it present in the analyte, the shift will still be very small and it's hard to detect. So we asked ourselves the question, can we add some other amplification? Can we add biological amplification and optical amplification without increasing detection time and complexity of the process? So we looked again at the PCR test and other tests which use biological recognition and biological amplification in some cases as a mechanism. So what is actually the signal that is read out in the PCR test? The signal is fluorescence. So every time a new DNA is formed by adding these complementary chains at every multiplication step, some fluorophore is released in the mix. And it starts emitting light, and intensity of this light is something that is detected by the optical detector. And why it happens? Because every time when this step of forming a complementary chain is run, it cuts a link in between this fluorophore and something that's called quencher that's attached to it. And it quenches the signal. So unless you cut this link, and this link cut happens at the multiplication step, you don't see the signal. Once the fluorophore is released into the solution, you can see it. So, and more of it is being released, the signal keeps increasing. And that's why after 30 or 40 cycles of PCR, detector can reliably see a lot of light and detect the presence of the COVID. So, but in this case, it's not amplification, it's actually suppression, which is then removed. And we felt we could do better. It's always better to amplify rather than just suppress and then return it to the original situation. So the new approach we're trying to pursue We call it high contrast probe detection. So we suggest to completely reverse the situation. Instead of trying to capture very little material that is present in the sample, may or may not be present in the sample, we want to functionalize our sensor with some very high contrast probes. So these probes could be metal nanoparticles or quantum dots, or something large enough and generating such a big optical signal that even if you remove just one of these probes, or especially if you remove many of them, you for sure will have a signal that's above the noise. Because again, if you just capture one molecule, one object, it may not be enough signal to be above the noise. So that's why you need a certain amount of material present. In this case, because we choose what particles we put on the sensor, we can choose them such that even a single one will be detectable. And so this idea came from Mike Dubrovsky, who is a student at MIT and also a co-founder of CFOX, a startup in Cambridge. So again, we try to make new sensors which combine high sensitivity from photonic detection and biological amplification, and they work this way. So we have some high sensitivity platform, a microring resonator, for example, which is seeded with high contrast probes. And then we somehow activate an enzyme, for example, to cut these probes. And this is the signal we measure, the signal generated by cutting. So how can we do this? How we can activate something to generate cutting? So for this, we are trying to use the CRISPR technology. So this technology is something that's already developed, and in the next couple of slides, I will guide you through the details. So it works like this. So this CRISPR complex is activated. It can be tuned to be activated only by a certain target RNA, which in this case could be COVID-19 RNA. And once it gets activated, it cuts any RNA or DNA, or RNA in this case, it can find a single-threaded DNA, regardless of whether it's target or something else. And so CRISPR technology is something that existed for a while, and usually it's used for targeted DNA cutting to create new targeted DNA fragments, and usually it's very specific. So it cuts only specific types of DNA, and that's why it can be used in this kind of technology. But there is one type or several types of CRISPR systems that after they get activated by a target RNA or DNA, they actually go berserk and start cutting everything else. So it's like collateral cleavage, which does not need to be the same RNA as present in the virus. And so going back to our situation, so in this case, it will cut also these RNA strands that attach our probes to the detector. And it means that even if you activate one complex, and you can get this complex in the close proximity of the sensor, it may actually cut thousands of probes. And it would be enough to have just one viral particle to get it activated. So that's where the amplification step comes from. And there are already some sensors that, biosensors that use this collateral cleavage mechanism, but they still rely on the biological amplification before they do the detection. We want to completely avoid this biological amplification step to make the time from the test to the result much faster, because you can precede your sensor with those probes before the patient even steps through the door. So this is done before. And then once the sample gets into the sensor, the testing itself can be really quick. It can be done real time, avoiding completely this amplification step. So we have some first data. I cannot show you the data with COVID yet, although we already have some first promising data. But to start with, we chose molecules which are not quite that deadly and can be done in any lab. So we seeded the ring resonator with probes. And in this case, the probes were quantum dots, and they were attached to the surface of the sensor through some multi-stage chemistry, which is a very standard chemistry already known. So this is important because you do not to devise a new step, a new type of chemistry to capture any new virus. Because if tomorrow you have COV3 emerging, or 5, or 10, or some other type of virus, Ebola, you don't need to redesign all this chemistry, which is usually a very time-consuming and difficult step in designing new sensor technique. You can use completely the same chemistry. You just need to train that CRISPR system to be activated by the new virus, and everything else is the same. And so in this case, we use quantum dots. Then we introduced DNase, not CRISPR in this case, but a similar enzyme that cuts through the DNA chains. And we could detect indeed the shift of the resonance in the ring because of cutting of the DNA. If we were just trying to wash it off with water, because this bond existed and the bond was not cut, there was no change in the spectrum. So we can see that we can reliably detect this signal that is caused by cleavage instead of addition of material. And this shift is actually huge. So this can be very easily distinguished from the noise, and it creates no problem in detection. Then we didn't stop there, and we looked at another platform. So this is work that's done at University of Vanderbilt, mostly with the help of the rest of the team. And Rabia, a student in this case who is leading this research project, so she used another platform. She used a very standard reflectance interferometry platform based on porous silicon. So this is a platform very similar to the one currently used by the European project to detect COVID virus in the standard absorption mechanism. So it works if you illuminate it with, so this one is interrogated vertically. So you come with the light bounces off, and you can measure the signal that emerges. And if you can attach or remove particles from the surface of this layer or from the volume of this layer, you can have a change in the signal. So we use the same functionalization technique. And as you add all this chemistry, there is a shift in the interference fringes. And as we add quantum dots, that shift is even larger. But as we cut them, the spectrum goes back almost to the original position. So the red one is after we introduce the quantum dots. So in the actual clinical testing, that would be a step done before the sensor even gets to the hands of whoever is going to perform the test. So that will be the initial stage. And then when the sample with the virus or whatever we're trying to sense is introduced into the system, this cleavage happens and the spectrum shifts, and that's something that you can detect. In this case, we chose quantum dots because this provides another signal that you can measure independently. Because when you wash away all those cleaved quantum dots, you can collect them and look at how much fluorescent signal is coming from this mix. So similar to the testing done for PCR. But in principle, once it's used for calibration, this step will no longer be needed. You can just monitor the spectral shifts and get the information that way. And we're working on new types of sensors to design them even better. And in the last minute or so, I just want to touch on the other challenge that we did not forget about, the microplastic, even though COVID happened. And here we're pursuing a totally different approach yet again. Instead of trying to sense it better, we're trying to prevent it. And what my group is doing, we're designing new types of plastics, which have a lot of practical functionalities, but also they can be made from the trash, from plastic bags that now get into the ocean and produce the plastic pollution. And also we're trying to design this material to create as little pollution as possible. And we're working with companies making plastic, testing different types of plastic to make sure that the result has the lowest pollution footprint. So I'll just skip through the next end and show you the last one. So we found interestingly that our material actually prevents bacterial growth on it. And we're hoping to modify it further to prevent viral, to provide viral protection too. So then it can hopefully prevent from viruses as well instead of again, testing, we can do prevention. And I'll be happy to discuss in more details any of these research directions, and I'll be happy to answer any questions you have right now.
Svetlana, thank you very much. I send you the physical and the virtual clapping. Thank you for the inspiring work. Participants, please type your questions in the Q&A, but let me kick one off. Maybe going back to like the biosensors. Yeah, what do you see as some of the biggest challenges with I'll call it scale up, but sort of with the manufacturing issues associated with sort of applying those techniques at scale?
Well, that's why actually we chose this technique, because we know it can be deployed at scale. Because again, if I go back to the slide I had here, we know that it's doable now with the existing technology. So we're piggybacking on the existing technology that's there mostly for semiconductor electronics industry, but it's already there. So nobody needs to build a new factory to start making these sensors. And you can, so actually how Siphex works, we do a lot of designs. They transfer these designs into the map outs, and then they send it to the foundry. So you don't need to build your own fabrication. You just need to come up with the new system design. And then of course you need to run the test by adding all these chemistry steps and cutting. But again, the procedures, some of them are very, very standard. So you don't need again to design anything new. So that's the beauty of it. And we're hoping, because unfortunately that's probably not the last pandemic. And if the next threat comes, there will be already a platform in place that can be very easily tweaked for a new challenge.
Very good, thank you.
But a very good question.
There's a question here from one of the attendees. What's the basis of the bacterial killing of the smart fabrics? Is it some ROS releasing materials?
Right, so right now, actually, we don't have any mechanism for killing bacteria. We just prevent it from growing and forming colonies. So the way it works is multifold. Some of it we don't even completely understand yet. So one way is because our fabrics provide passive cooling through radiation, conduction, and evaporation. So what it does, it reduces the temperature, and it also removes all the water humidity very quickly. And this is not good for bacteria because they like it warm and humid, of course. So this inhibits bacterial growth. And we measured it relative to, if I can go there, we measured it relative to other fabrics, and we were surprised to see how much slower is the bacterial growth. So this is a growth in 24 hours. And cotton is usually considered the best material because it is very little growth. But our recent testing showed that our material exhibits the same amount of growth as cotton, which is significantly smaller than everything else, which is very encouraging. But now we're doping material with, so this is, for example, doped polyethylene. It's not white anymore because it is stuff we put inside. We're doping it with known antibacterial and antiviral particles, which in many cases are just simple metal oxides, which get activated by UV portion of sunlight, for example, and they literally kill then viruses and bacteria. So that's like the next step we're working on.
Very good.
But yeah, I have a question about calibration.
Yes.
Whether it will be needed before real-time measurement. I presume this is for COVID sensing. And yes, of course, like with any sensor, calibration will be needed. That's the steps that we're going through now, exactly. So, because our concern now that the sensing could be too sensitive, because if we need to really calibrate how much of the probes are cut, so how many, for example, we put to start with, because we're afraid that it may be such a drastic change in the signal that it will take this sensor from the dynamic range. So it's not a usual problem for sensing. Usually you are trying to amplify and calibrate it that way. But yeah, absolutely. In any case, you need calibration first before the sensor can be released, even for research use, let alone for clinical use.
Let me ask another question came in, but let me ask a question on the computation side. So the sensor side, in terms of relying on photonics or silicon and sort of conventional fabrication processes, what about on getting the data off? What are the issues associated with communicating the results and
Right, yeah, because these sensors are used completely based on optical readout. So again, there is already everything existing for this. So right now, what we're doing, bringing signal in and out is through fibers, and then fiber goes into the detector, or fiber brings the signal from the laser. But in the long term, the company is trying to put everything on the chip, so everything will be completely integrated. So that's the beauty for the end user. So you would have a chip that does everything. There is an integrated laser source or LED source, and then integrated detector. And you just need to spit into some window on that and wait for 10 minutes or so to get the result out. So again, this is a beauty of existing technology, because a lot of these elements already exist for electronics.
I'll ask you to take somebody chatted me a direct question in terms of the recycling or the ability to dispose of once you have a contaminated sensor. Is it, and if we're using hundreds of thousands, if not millions of them, is that an environmental concern, or what are the constraints there?
Well, here again, I think we could probably piggyback on the silicon solar cell industry, because it would face the same challenge. There is a lot of material to be recycled. But again, most of this material will be silicon, which is a pretty benign material, and or any other silicon semiconductor electronics. It uses the same type of chips. So if there is any pipeline, I actually don't know if there is a good pipeline for recycling, but if it's not, it should be designed regardless of whether the sensors are deployed or not, because there is so much of that material already out there. And then it can go into the same recycling cycle.
Very good. So I think attendees, please, if you have any other questions, feel free to chat them directly if you want, or the Q&A.
Yeah,
there was a follow-up question on maybe a comment. If it's on, is related to the calibration, but probably materials involved will not be so stable in their properties, or that was a ... So what are some comments on the stability of materials?
Right. So that's again something that will need to be tested, and that's right. Every sensor that's already prepackaged with some material, even tests that are available now, they have shelf life. So yeah, that will need to be estimated, and probably that would require involvement of other people, because that's not my field. How to you increase the shelf life of the sensors? Yeah, these are absolutely valid questions. But in this case, it could mean, when we need so many of them, it just means somebody spends 2 hours preparing it before it gets to the testing site, and it does not require too much life on the shelf, because we need them now. So it's not an immediate problem. But if we store them for the next pandemic, then yeah, that would become a more significant problem.
Very good. I think with that, participants, thank you for your attendance. And Svetlana, thank you for the presentation and the phenomenal work. And I look forward to hearing more about it. Colleagues and all, please join us next week, same time, same channel, for the next MECI Alliance seminar series, where we'll have Professor Ahmed speaking about automated discovery of high quality novel designs and sharing a little bit about his work. And please, this is an open seminar. We want to engage the community, our faculty, our students, and our collaborators and partners. So if there is a speaker that you'd like to hear from, or if you would like to nominate yourself, do please send us an email, and we'll work with you to coordinate a time to hear the words from the community members that you would like to hear from. So Svetlana, a good thank you very much. Teresa, thank you for kicking it off at the beginning.
Absolutely. Thanks, Brian. Thanks, Svetlana. Have a great day.
Everybody stay safe and see you next week.